So welcome to this MaLGa seminar. Today we have a guest of honor. It's at the same time a pleasure and an honor to have Tomaso Poggio. So I guess quite a few of you might know Tommy personally. Probably more or less all of you know him by fame. I was trying to sneak on his Wikipedia to give you a summary. It's not the easiest thing to be concise because Tommy has been doing a lot of things, a lot of different things in a very good way. So the list of prizes is pretty long. The list of honors is pretty long. So I'll just say this: it is a list. The list is long. Okay. Maybe what I'm going to tell you is that he's very wide in his interest. The general theme is understanding intelligence, both in humans and machines, and how the two things are related. And he has I think he has a unique, very wide view on the topics of intelligence, not necessarily only artificial intelligence, but he also has zoomed in time in topics where he went very much in depth. And I guess one of them, at least the one that brought me close and to read this paper, is the theoretical aspects of intelligence and mathematical intelligence, in particular in connection to the problem of learning, okay, as one of the gateway to understand intelligence, and where he has many great contribution. I guess the role of regularization, the general idea of ill-posedness in the context of machine learning, and not only. So there are many famous papers. Collaboration with Federico Girosi and Steve Smail and others. I guess the talk today, as we're going to hear, is about some updates of this idea in view of some of the recent discoveries. I think he's been very dynamic in adapting, probably more than me, for example. You often make fun of me because I've not updated my learning from 10 years ago, but he did, and so today I think he's going to give us a fresh view, and I hope you will all enjoy it. Okay, thanks, Tommy.
Well, thank you, Lorenzo. This was supposed to be informal. I thought I will use you as a soundboard for some ideas, and some are wrong, so please tell me. And these are some thoughts. I take full responsibility for it. They come out of discussions with several people, especially Lorenzo, but I did not want to keep you responsible for anything. So, okay, the question is, right now, it seems to me in the field of machine learning, well, there are two things. One is this question. Even before, I have to say that it's totally unclear at the moment whether theory will be helpful at all in the future or not. So far, in the current revolution about deep networks and so on, it has not been. And so the field is driven by hackers and programmers. And so it's a big challenge whether we'll end up in a future in which theory will not be needed anymore because computers are powerful enough to run simulations, and the end of theory. Could be. I hope it's not. But anyway. But if we look at theory and try to work on it, one of the questions right now is about common principles of different architectures that seem to work well. One is the brain, the human brain, of course, but other ones are convolutional networks. And in the last 2-4 years, there are several other network architectures, transformer, perceivers, MLP mixers, which also work very well. For instance, transformers trained on 0.5 terabyte of data can solve all the mathematics problem in the main courses at MIT. 100%. This is a paper of Jill Strang in PNAS. Pretty impressive. So you formulate the problem in like a standard problem in English language plus equation, and you get an answer. You may have to reformulate it in some cases in a slightly different way, more precise. But so quite impressive. So there is this other question about which I will not speak about, which is if at some point a transformer becomes conscious, how will we know? But that's a bit of science fiction. But anyway, the question is, among all this architecture, maybe there is a common principle why they work so well. And so let's try to formulate this question a bit more precisely. First of all, this is a typical example of a shallow network, one layer of weights that are trainable is a kernel machine. And then we have architecture like convolutional networks, very deep convolutional networks with skip connections. This will be like REST nets. And a formalization of networks like this is, in terms of a corresponding function graphs, could be a binary tree in which the local so-called kernel of this network will have a dimensionality of 2. Each of the nodes in this binary tree is a function of 2 variables. So this is kind of an abstraction of convolutional networks. And in the case of actual convolution, there will be what would be equivalent to weight sharing, which means all the function at one level, say the first level, for instance, these functions, each of these dots is a function. All these functions in the case of convolution and weight sharing will be the same, and all these functions will be the same. Okay, so that's the case of CNN, and in this case, we can look at what happens first from the point of view of representation, which kind of input-output mappings can networks of this type that have a function graph like this, which type of function they can represent. And one knows since the 80s that one-layer networks like kernel machines is a universal approximator. So if you have a continuous function on a compact domain, you can approximate this function arbitrarily well by networks which have one layer of weights, and with nonlinearities, the activation nonlinearity, which is nonlinear and cannot be a polynomial, but otherwise, pretty much everything goes. So this is a kind of Weierstrass theorem for networks. So in this case, having a deeper networks does not seem to help. You can already approximate everything with one hidden layer network. But if you look a bit more carefully, you find that, yes, you can approximate everything, but at the expense of a number of parameters can be very large. So an upper bound on the number of parameters you need to have an approximation in the order of epsilon, say in the sup norm, is in the order of epsilon to the minus d, where d is the dimensionality of the function, for instance, 8 in this case. So, if epsilon, say, is 1/10, So 10% error in approximation. D is 10. This number is 10 to the 10. That starts to be pretty large, especially because D, I said, is 10, but if D is the number of pixels in an image, like 200,000, you have 10 to the 200,000, which is really a large number. It's much more than number of electrons in the universe. Okay, so this curse of dimensionality is well known, and it's a real problem. And by the way, this, let me skip this, but the way to prove this approximation is essentially using polynomial approximation of the nonlinearity, and you end up using polynomials to approximate the nonlinearity produces the powers you need, the products between the monomials and so on. With RLU, a smooth RLU will give you the same thing. In addition, using depth, you can obtain the nonlinear parts of a polynomial using this kind of arguments that is due to Jarodsky, but it's not important for what I'm going to say. Okay, so what is interesting is, at least for me, since we found this, is that if you have a generic function, the only way I know that you can use to counteract the curse of dimensionality is smoothness. So in fact, if we go back to this, this bound will be d over m, where m is some measure of smoothness, like in a Sobolev space, or number of derivatives with finite norm. And so increasing the smoothness will counteract this curse of dimensionality. But the other way in which you can counteract this curse of dimensionality is to make some assumption about the class of functions. And one in particular is that you have functions that are compositional, functions of functions of functions. And one nice example is the one that come out from essentially the same binary tree I showed before, which is a function, in this case, is a function of 8 variables, but it's really the composition of functions, each one of which is a function of 2 variables. And in this case, it turns out that the number of variables that essentially sets the rate of approximation is not 8, but is 2, the dimension and dimensionality of the constituent function. And so by using compositions of this type, you can have functions that are have an arbitrarily large dimensionality, but where the constituent function have only dimension 2, or some other fixed or bounded dimensionality. And in this case, in the case of a function that has a function graph, so it's a function that is composition of different functions. Each function is this red dot, and functions are, so each function here is a function of 2 variables. And in this case, instead of having this upper bound for approximation, you have an upper bound which is like this. So it's essentially, apart from a constant factor, linear in the dimensionality. So it does not, you avoid the curse of dimensionality. And first of all, it's interesting that in the proof of this result, which is pretty simple, but what is important is the fact that the constituent functions have a bounded dimensionality 2 in this case. This is what avoids the curse of dimensionality. If in addition you have weight sharing, which corresponds to convolution, then as I said, this means same function here, 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 and here. And of course, this will also reduce the number of parameters, but not in an exponential way. So convolutional graphs are a special case of this. Okay, so, and you can extend this result to arbitrary directed acyclic graphs like these ones. And essentially the dimensionality of a function that is the composition of a number of functions would be given by the constituent function that has the largest number of inputs, the largest dimensionality. So in this case, I guess, would be this one, the 4. Okay, this one. Okay, so here we so the details are not so important. The main message, as I said, is that the number of parameters really depend on the constituent function with the largest dimensionality and the smallest smoothness. Okay. So this says that for target functions that you want to approximate, input-output mapping, then deep networks can help a lot from the approximation point of view if the target function has this compositional structure. And many functions are have this compositional structure, or more than one. It's the compositional representation of a function is not unique. There are functions that cannot be easily decomposed with constituent functions that have lower dimensionality, or like in the case of a polynomial, then you have a lot of terms. So you don't gain anything if the polynomial is not sparse. But I found personally difficult to think about functions that are high dimensional and not compositional. And most of the functions that we use and are defined on a computer, for instance, are composition of some basic function, from multiplications and addition to some of the basic function like exponential and sinusoid and cosine and so on. So it's probably not a bad assumption that in many cases input-output mappings may have a compositional function that is nice, where constituent functions have a lower dimensionality. But to characterize this better, it's an open question. And it's kind of intuitive that problems like speech and text are compositional in terms of how they are generated, because they are the composition of, for instance, text of letters into words, into sentences, into paragraphs, into stories. And you may make a similar argument for images, although in this case it's a bit more difficult to argue why it should be that way. But you don't need to, in order to recognize a picture, you may not need to have this pixel interact with this pixel and this one from the very beginning. You may compute first local predicate, like the objects in one place and object in another place, and then combine them, and this corresponds to a compositional function. Okay, but of course, learning is not only approximation. There is also the question of generalization. You have data, you want to learn a function, you can learn the parameters. You have to have a guarantee that you can generalize to new data from the same distribution. And so in this case, there are a couple of papers, and I think Lorenzo told me about it, from statisticians that essentially say that so again, also for learning, the key assumption is that the target function is essentially sparse. So that is like it's a bit more general, but are functions like similar to the ones that is described over there by the binary tree. So that depends on constituent functions that have a smaller dimensionality. And if you have a target function of this type, then approximation works. And if your empirical risk minimization also works, that's an assumption, then you have generalization. But a big assumption in this work, which is very recent, is that your network are under-parameterized. You have more data. You have essentially an arbitrary number of data. Whereas in current deep learning practice, typically the situation is the opposite, in which you have a total number of parameter W, which is actually much larger than the number of data. So, okay, I'll come back to this. But one question is exactly whether we still have generalization, whether these results can be extended to this case. And of course, the first question is what happens when you do empirical risk minimization in this case? Because now you have an over-parameterized problem, and in this case, if we look at the example, for instance, of starting with kernel machines, and is that you have more parameters, but the number of parameters really does not count if you have appropriate regularization. Essentially, what here is important is the complexity of the solution, and if there is an appropriate explicit or implicit regularization, even in the over-parameterized case, you may essentially find a solution that generalizes. In the linear case, this would be finding a minimum norm solution if you are over-parameterized. And the minimum norm could be through regularization term or implicitly through properties of gradient descent, as Lorenzo and Silvia have shown, right? Okay, so support, this is a conjecture, and in support of a conjecture, there is the linear case. So in don't have a regularization term, but you have initialization with zero norm, ideally, minimum small norm, the gradient descent will converge to a minimum norm solution. For RLU multi-layer networks, so standard networks like convolutional networks, we find, I can speak about it if there is time, probably not, but we find a similar situation in which there is, with gradient descent, there is a convergence to the solution with a minimum rho, which is the product of the Frobenius norm of the weight matrices across layer. Again, for small initialization, or if you have small initialization and a regularization term. And then you can use a standard generalization bound to show that the solution with the smallest rho are the one which have the best bound on the generalization arrow. So okay, this is so far so good, although a number of these things have to be proven. The network we have analyzed is are networks of this type, where you have multiple layers, you have the RLU, you have an algorithm, in our case use Lagrange multiplier to normalize to 1 the norm of each layer, apart the last one. And the last one, you can think of it as unconstrained in terms of the norm, so it's a normalized vector, the last layer, it's linear, vector time a scalar rho. And so the optimization on all the VK at every layer and rho gives with small initialization a minimum rho solution that can interpolate the data if this is overparameterized. We have still to do some, we've done experiments supporting the analysis in the case in which we have used batch norm instead of Lagrange multiplier. We're now doing experiments in which we use Lagrange multiplier. And okay, so the one thing that it's completely open and is the fact that empirically it seems that if you try to learn classification on images, like ImageNet or so, then overparameterized convolutional networks perform better than, or much better than, dense networks. And this is not really explained from what I said. If we assume that the Langer result is valid because of a bias in the norm, in rho, also for n less than W, unless we assume that, yeah, but we have to explain why, that ERM does not always work in the case of dense network. This potential explanation is supported by a relatively recent result by Eran Malak and Shai Shalev Schwartz, in which they show that there is a class of problems which is to detect K patterns, which is a string of K bits embedded in a larger one, so specific K-bit pattern. And they show that this problem can be efficiently solved using convolutional networks trained with gradient descent, but cannot be solved because of computational complexity if you use a dense network. And so this hints to the fact that ERM may have problems with dense networks. Another point of view that is be also interesting to think about is this lottery ticket hypothesis. It seems that you can, given a big network, and you know that there is, you can, let's see, I'm simplifying a lot, but is you can find a smaller network, it's like pruning the big network, that will work as well or potentially better. Right? But this problem is as hard, the problem of pruning, of finding this subnetwork, can be very hard. It is at least as hard as training from the beginning a network that does well on the same pattern. So, so there are some interesting hints that the optimization problem may be computationally too complicated or very complicated for dense networks. Okay, so some more words in on the convolutional networks, especially transformers. So in a sense, you can think of convolutional networks as a situation in which you assume you know what is the graph of the function that you want to approximate. Because you're using a network in which you know that x1 and x2 are next to each other, they interact with each other. The kernel of the network will give you this relation of these neighborhoods, and so you know this, maybe approximately, but you know this. So locality, the fact that you have a sparse representation, you essentially assume it by using a CNN, and you go on and you use them. The case of transformer, the assumption is that they also work for the same reason, because you have effectively not all the dimensionality of an image, but a much smaller dimensionality. But there you don't have an architecture that defines locality. What happens is that there is a first step in the transformer computation, which is called self-attention. And this is essentially a linear operation that finds, for a given token on which you are sitting, finds the other tokens that are most correlated with it. And I think that this is an hypothesis that this self-attention operation, which is followed by a soft max, so this essentially selects the tokens that are most correlated with the tokens you are evaluating at the moment. The token, by the way, can be one pixel, one small set of pixels, one word, parts of words, or is that this self-attention operation, I think, this is just conjecture, is equivalent to finding the best linear approximation to the mapping you are trying to learn. And so suppose that this linear approximation gives you information about the relevant variables, the relevant pixel. And suppose that the overall function that you are trying to learn consists of it's a compositional function, but the variables that are important for the linear terms are the ones important also for the other parts of the function. And then optimization should be easy. Let me explain what I mean. This is an idea that comes from a recent paper just a few months ago by a group of Guy Bretzler. And the paper is about Boolean variables. And they define Boolean function with the staircase property. The definition is a bit complicated, but here you have an examples in which you have a Boolean variable, so x1, x2, x3 are either 0 or 1. And if a function, a staircase function is a function where the variables in the linear term, you have, you're missing here x1, there will be an x2. This would be that the variables in the linear terms also appear in the other terms. And so a simple thing to say for trying to extend this is that if you find first the linear terms, then you know what variables are important. For this type of function, you know that the second order terms, x1 square, x1, x2, etc., will contain only the ones in the linear terms and not other ones. And so the optimization is much easier. In this particular paper, they have an algorithm that does efficiently optimization, essentially searching first the linear term and then the quadratic ones and then the other ones. And it works efficiently because it knows that the only quadratic terms are the ones that contain the linear variables. So, so I think this would be a possible extension. It is a function where the linear terms tell you the variables that are relevant for the function. And for instance, if you have a function which is a composition and you have a linear term here, then all the other functions will depend on the variables that are important for G1. For instance, if G1 does not depend on some of the initial variables, then also G2, G3, all the other ones will not depend on those. So all of this has proofs that have to be really written down. An interesting point, I'll just is a footnote, but is that for functions that have this structure, it should be fairly easy to do learning using layer-wise optimization. This is finding, let me go back here, is having different layers in deep networks and optimizing one layer at a time, keeping fixed all the other ones. This is also alternating optimization or so. I'll not tell you more about it because we have not done enough work or experiments on it, but it seems, if this is true, and there are some empirical evidence that you could efficiently learn this type of functions by layer-wise optimization, then you don't need backpropagation, and that would make this very attractive from a neuroscience point of view, because what is implausible for neuroscience in backpropagation is the fact that you have to communicate gradients across many different layers. It's difficult to imagine neurons can do that. But here you'd have only local learning. At each layer you have, if you have an error signal from the top, then it's all local. You don't have to send, could use a perceptron learning rule, essentially, which would be, from the neuroscience point of view, quite attractive. And so, in summary, the idea would be that the key part is really the fact that the function you want to learn has this compositional structure with constituent functions that are low dimensional. And that make approximation easy, the representation issue in terms of avoiding the curse of dimensionality, or at least the worst effect of the curse of dimensionality. And then it will also make ERM work and optimization work. So that's kind of the big claim in this conjecture. Whether that's exactly true, it's unlikely, but these are things to be interesting to explore. And so if anybody who gets some results, please tell me. I'll be curious to know. Okay. Maybe I should stop here. I can tell you more about what we have done in terms of an analysis of gradient descent in the multi-layer network, but it would be a bit too involved. So, thank you.
For questions, you can run with the mic if anybody has questions.
Thanks, Tommy, for a very interesting talk, very fascinating. So I didn't understand many things, but so one question I wanted to ask is, at some point you spoke about minimum norm interpolation, and I didn't understand how you define norms for these nonlinear functions. So you have this row.
Yeah.
So I understand for kernel machines, you do minimum norm interpolation, it works well. But what about these deep networks? Yes. So there's one question.
Yes. So this is this case here in which we have a deep network when we are using square laws, but the yn are classification, for instance, a binary classification, +1 or -1. If you have enough over-parameterization, empirically you can fit the data, interpolate. And theoretically there is this theorem by Ian Cooper that essentially tells you that in the case of over-parameterization with smooth RLU, you can expect a degenerate set of global minima corresponding to zero loss. Degenerate meaning, because W is larger than N, the dimensionality of this zero is W minus N, possibly large. In addition, there are some other results saying that this global minima, that is zero loss, so interpolation of all the points, are all connected in a large valley. Okay, so of course you have a lot of degenerate solution in this case. It turns out that if you, let's see, if you look at your function represented by the network, you can write it as, let me see if I have it here, as it's essentially, you can write it as the product of a scalar number, rho, times the function produced by the same network, but where the weight matrices are all normalized to Frobenius norm 1. Okay? So you can think of rho as the product of this. Often people use a regularization term in weight decay when they optimize deep networks. This would correspond to regularization terms in rho. If we have this, then the gradient descent will, starting from small initialization, will converge to quasi-interpolation. If we have a regularization term, will not be exact interpolation. And they will essentially try to minimize rho. Not clear this always happen because I can go into more detail about the landscape of the error, but there will be a tendency for small rho, and you can use let's see. Photo slides. Yes, you can use generalization bounds of this type. So this would be the expected error. This is the empirical error, which is 0 if you have interpolation or quasi-interpolation. And then you have a term that depends on the Rademacher complexity. And this is because of the RLUs, this rho can be pulled out.
Rho is inside the Rademacher complexity.
This product of the norm. This, and so you end up showing that if you have interpolated solution with different rhos, the one with the smallest rho has a better bound on. It does not necessarily have a better generalization error. Does have a better bound on the generalization error.
But rho is a norm or is a.
So this would be like
something else.
Is the product of the norms
of the weight
matrices.
Yeah. But so this is for
the product with the smallest.
Is for linear. Is for linear activation function or for any activation function?
For
any. Yeah, okay. Yeah.
They have to be homogeneous. So RLU.
Yeah.
Sigmoid does not work, but RLU do. Yeah. So this is that is not a norm, but be the equivalent of the norm in the linear case.
Okay. Thanks.
Other questions?
Thank you very much for the talk. I was wondering, so this the state of neuroscience is now changing entirely because of data. And I was wondering if you can comment on how all of these ideas can quantitatively be tested on neural data. Now we have architectures, at least for some species. Is there a way to know if the brain functions in any ways similar to how this deep network works?
Yeah, that's an interesting question. So there is work by a colleague of mine, Jim DiCarlo, which has been become quite popular, and there they have there is a website, there is even a competition right now. They have this metric called brain score, in which they score models, like different types of deep networks, in how well they reproduce data from neurons in visual cortex. So I'm a bit skeptical, and the reason is because it's really kind of, performance-based, and does not take into account a lot of the details of how different operation may be implemented or not by neurons. They don't say what is the RLU in neurons, right? Similar things. So I think, and a lot of this is really fitting data, essentially. Typically, neuroscience, the golden standard for a theory is to be predictive. Make a prediction which is ideally a bit surprising. You do the experiment and you falsify or verify. And the way things are going, that's not. So, I'm on the physicist side, and this is more on data fitting, which is not completely useless, but I doubt very much that models developed by engineers like AlexNet happens to be exactly what visual cortex is doing. I'll be very, very surprised. There are more specific criticisms. If you look at brain scores, after you train, it depends more on the data than on the architecture. What is actually interesting is to compare architecture which are not trained. There is anyway, that's more like system identification, but that's a separate discussion. So I don't know if I answered your question, but I think there is there are a lot of things that are more interesting in neuroscience. I think, for instance, the way I would like to do this is to abstract principle ideally from theory and praxis of neural network, and see how they can interpret them in, say, visual cortex or other parts of the brain, like this idea of dimensionality reduction for making possible approximation and optimization. Or the idea, backpropagation is biologically plausible. Can we come up with a biologically plausible alternative?
Okay, thank you again for the talk. And I don't know if my question makes any sense. Anyway, if I understood it right, you said that the deep networks can represent and therefore recognize only the compositional functions.
Well, yeah.
Okay, but my question would be, does it give us any hint on the phenomena that could escape this kind of artificial intelligence? Or can it be exploited, for instance, for, I don't know, using non-compositional functions for encrypting or doing something that cannot be recognized or broken by this kind of networks?
That's a very good question. There is potentially this question: why compositional functions, right? Or compositional function with this nice structure? Why are they so important? One possible answer is problems like understanding text or speech or recognizing images are things that we do. If you look at our brain, for instance, visual cortex, you see that there is this organization which is like a convolutional type networks in which a small number, forget small number, ganglion cells look at small number of photoreceptors, and cells in V1 look at a small number of ganglion cells, and so on. It's like the binary tree I showed. So you could say, okay, evolution does short-range connections because this is what is easy to do with neurons and synapses and so on. And then it created networks that can easily solve these compositional, solve these compositional tasks or functions. And so the fact that these are probably interesting for us would be because our brain has been evolved to solve this kind of problems. There are a number of problems, say, predicting the stock market based on a lot of financial variables. It's not obvious what immediately what the concept of locality there would be. So a convolutional type approach would be very difficult. One can, I'm sure, come up with other tasks that are possibly not compositional or not easily solved. But it's a very interesting
Thanks.
question.
I keep touching upon this thing, in maybe slightly, maybe the same or a slightly different way. What is, you think that, it seems to me that, and I want to hear from you what you think about it, that the examples that we make about seeing, listening, speaking, or even in the animal version, which is almost equivalent, reflects, seems to be hardwired in a sense. So the structure of the signal seems to be well caught by the type of networks that are described. And maybe the compositional structure, I wonder whether you think that the compositional structure is the answer, or is sort of the right structure for addressing these problems. And in a little sort of similar way to what Enrico asked, would this be the answer of why it is so difficult to solve problems of different nature that has little to do with perception, like you mentioned the stock market, and I think about several very interesting problems that we still have, and I don't, despite the widespread enthusiasm about deep networks, I think that there might be even give a little hope that why theory might have a shot in the future for addressing this more, I wouldn't say more complex problem, but problems that probably evolution didn't think about. Is that nonsense?
Yeah, so I made this claim, which is a claim, it's a conjecture, is that the compositional structure is important not only for approximation but also for optimization and generalization. Yeah, I don't know whether that's true or not, and we'll see. Right now, from thinking about what I think, it seems to me one possible way to understand the success of these different architectures, but I cannot say it for sure. And in terms of evolution, I don't know. It depends how important or widespread are non-compositional functions. if you think about, for instance, maybe some of you has some good idea, but say polynomials, right? Take a polynomial of degree k in d variable. This has in the order of d to the k monomials, or k to the d, depending on the approximation you're using for the binomial. So it's a very large number, and are they all important in practical cases? Describing physics or other problems. If you find this is kind of I don't know.
I have a curiosity more on the mathematical side. So you mentioned that under certain assumptions, ERM works and so goes towards a global minimizer. I was wondering what are the structure, why is it so? Since the function is non-convex, what is the reason of why I'm going towards a global minimizer? That is not true, for instance, I don't know if instead so you mentioned these works, if I understood correctly, for instance, for sparse networks, while it's not true for dense networks. So what is the difference in the structure of these networks that make a minimization approach work in one case and not in the other?
So we are speaking about gradient descent, I guess. So there are, let's see, there are some results that say that if, let's see, let me try to, that the loss function has so, okay, this is an intuition, no more than intuition, but imagine a non-convex problem, but one in which there is a linear part in the loss function that so that the gradient will be directed to the minimum, even if it's not right there. So you have a landscape which may be like this, but the absolute minimum is here. Another one which is completely flat and has a narrow hole. So, the second one, if you are in very high dimension, may be very difficult to solve. And this may be the case if you're trying to find a convolutional subnetwork, meaning local sparsely, within a dense network. Whereas other situations, like finding you have a convolutional network that is over-parameterized, but many of the parameters are redundant, and you have to find, in a sense, a minimum norm solution if you want. Maybe more similar to the first case. Now, this is I think the result, that one that I mentioned, this one of a class of problems detecting a K pattern, a particular sequence of bits within a large sequence, something that's easy to solve with convolutional network is not easy because of the complexity of optimization to solve with a dense network. It has this flavor. But this is just very, very superficial intuitions.
There are no questions. So I guess thanks, Tommy.